So we're going to combine sections 10.1 and 10.2 to look at the laws of sines and cosines. And those are essentially they're called laws, but they're really like identities or equations you can use in order to find the sides and sometimes the angles too of triangles that are oblique, so that are not right triangles. In the book, they use the following notation. For the angles, so beta, alpha, and gamma, opposite to beta. So beta is like the B in Greek. So we have side B. Okay, so opposite to beta is always side B. Opposite to alpha, which is essentially the letter A in our alphabet. Okay. We've got side A. Opposite to gamma, we've got side C. So that's always that notation that's used in the book. I will now draw a perpendicular from the vertex at angle gamma to side C, like that. And I'll call that H. That's for the height. And let's write down a few equalities. So for example, the sine of alpha, that's, if I look at this triangle here with side H, hypotenuse B, and angle alpha, it's a right triangle, okay, because H is the height of the triangle. So sine is opposite over hypotenuse, right? So in this case it's H over B, okay, which implies that H is B sine alpha if I solve the equation for H. If I look at sine of beta now, okay, but this time looking at this triangle with this beta, this right angle, this is H, this is A, so it corresponds to the inner right triangle. Sine of beta is opposite over hypotenuse, so it's H over A. So again, if you solve for H, you get that H is A sine of beta. Now equating, so the B sine alpha would be A sine beta together, because they're both equal to H, okay? So we get that H is, at the same time, it's B sine of alpha, but it's also A sine of beta, okay? So we're going to look at this equality now, and we're going to write it somehow differently. We're going to what we're going to do is we're going to multiply by B over A on both sides. No, let me take that back. We're going to divide by AB on both sides. Okay, essentially multiply by 1 over AB. And if we do this, we essentially get that this is sine of alpha over A. And this is sine of beta over B. So it's kind of nice to see this alpha goes with its opposite side. This beta goes with its opposite side. Okay. Since it's an oblique triangle, so none of the angles or the sides are anything special. So similarly, we could actually derive an identical expression, okay, to the previous two, which would be sine of gamma over its opposite side. Okay, so this is using a similar analysis. So to get that one, I would probably have to draw a different height for the triangle. But anyway, I would be able to derive this. And these three set of expressions are equal to each other. This is the law of sines. It helps us to solve for a triangle if we've got two angles and one side's missing sometimes. So we'll see in which context it applies, but it's going to be pretty obvious like when we want to use this. So we'll start with an example. So here's a triangle, and we're given two angles, 30 degrees, 50 degrees. So notice that none of the angles will actually be 90 degrees. We can easily find the other missing angle by subtracting from 180, 50, and 30. But here, so we could actually do that. Find this missing angle. We could call that beta, let's say, and this is going to be the side B that we're also going to try to find, and we're going to call that side, let's say, C. So we're going to find beta, C, and B. Beta is pretty easy, like I said. You do 180 degrees minus 30 degrees minus 50 degrees, and that gives us 100 degrees. Okay, all right, that was easy. How do we find C and B now? So now this is where you notice, oh, I've got 10, and I've got the opposite angle to 10. Okay, so I know the ratio of the sine of 50 over its opposite side. Okay, I know what that number is. And then after that, I've got an angle and a missing side. So this is where we can use the law of cosines. So look why that's the case. If I do sine of 50 degrees over its opposite side 10 is equal to the ratio of sine of 30 degrees divided by its opposite side. And then here I've got an inequality with one unknown, so it tells me that law of sines will allow me to find what C is. So solving for C gives me what? C is going to be sine of 30 degrees divided by sine of 50 degrees multiplied by 10. And if I evaluate this using my calculator, I get 6.53 for C. So this is 6.53 approximately. And then I can do pretty much the same to solve for B. So sine of 50 degrees over 10 is in the same ratio as sine of so for B I need beta, so that's okay. Sine of 100 degrees over B, and that tells me that B is going to be equal to sine of 50 degrees over sine of 100 degrees times 10, and that's going to give me approximately, oh, actually take that back, 50 should go at the bottom and 100 at the top, like that. Okay, that's better. And this is 12.86 approximately. And beta is 100 degrees. So you see I've solved for the triangle. I found all the sides, all the angles. Let's take a look at another example. This time, we don't have all the angles this time. We've got only one angle, 35 degrees. However, I know the measures of two sides, 8 and 6. We'll call that angle, let's say here, gamma, and this is beta. Okay. And I'd like you to notice something here. Beta on the figure seems to be acute. Okay, this will come into play at some point. So to find, let's say we call the missing side C, because it's opposite to gamma. So we can use the law of sines. You see I've got 35 and its opposite side. So I see that sine of 35 degrees over 6 is, and now I'm going to use beta and its opposite side. So sine of beta, which I don't know, over its opposite side 8. And therefore here I've got an equation with only one unknown, so I can try to solve this for beta. So sine of beta will be 8 divided by 6 times the sine of 35 degrees, which I can evaluate. This is approximately 0.7 0.65. And here, to calculate beta, I can take the arcsine. Okay, and I obtained 49.9 degrees. Okay, once I have beta, I can easily recover gamma, which is going to be 180 degrees minus 35 degrees minus 49.9 degrees. That's going to give me 95.1 degrees. Okay, so maybe I should write approximately because beta is approximate. So finally, having gamma in hand, I can find what C is. So I have sine of gamma over C is in the same ratio as sine of 35 degrees over 6. I could have used beta here, so I could have used sine of 49.9 degrees over 8. Okay, it's up to me to choose what I want, but 35 and 6 were exact on my figure, so I prefer to use that. Gamma is known, so okay, don't worry about it. I don't have two unknowns here, so I solve for C. So C is going to be sine of gamma over the sine of 35 degrees times 6. And this is approximately 10.42. So here I solve for all my sides and angles. So my triangle is essentially the following. This is 8, 6. This is 10.42. Beta is 49.9 degrees. This is 95.1 degrees. This is 100. What did I write? 100. This is 35 degrees. And those are all my angles and sides. Okay. Now let's take a look at a third example. And you'll see it's kind of similar to this one. So here I have this. 8, 6, 35 degrees again. So notice that the measures that I have here are the same that I have over there. So what's the difference between those two triangles? Okay, it's the fact that this angle here, beta here, is now obtuse. So in other words, if I look at the two triangles, okay, if I'm just given the information, like two sides are 8 and 6, and the one of the angles is 35, okay, 35 being not the angle between 8 and 6, that's kind of not enough to specify what that triangle is, because I can construct two triangles that are sort of similar, not similar, but that have carry the same information, okay. So, and the reason for that is that the triangle I have here, okay, I could move this side here, okay. Maybe let's do let me draw a better picture here. So think about this side as being 6, okay. I can, and maybe let's draw a horizontal line like that. I can actually, let's say this is 8 here, 6, 8. I can actually move this side here to create this sort of this isosceles triangle, okay, so that this is also of side 6, okay. This angle hasn't changed, right? Let's say this is 35. You actually see here, and maybe let me use a different color. This was our initial, well, the triangle in the previous example. And the one in yellow, or maybe I'll use a different color. The one in blue here is the one we currently have. And they both have one side that's 8, the other side 6, and the angle of 35 degrees. But obviously, some of the measures will be different. And that's due to the fact that I can either have a triangle with these measures with either an acute angle here or an obtuse angle here. So noticing that beta is acute or obtuse is kind of a big deal here. So we'll see how we can recover beta here, because I can't just carry the same analysis I had here. So basically here, with this beta, it was definitely acute, so I was on the right track. Okay, so if I'm trying to essentially replicate the computations I did previously, right? I could try to find what beta is. Say sine of beta over 8 is in the same ratio as sine of 35 degrees over 6, and then solve for beta, or sine of beta first maybe. Sine of beta will be 8 over 6 sine of 35. And so far I have the exact same steps as before, right? Sine 8 over 6 sine 35. I'm going to get 0.765 again. Okay, so exact same steps. Okay, problem is if I just say beta is simply the arcsine of 0.756, I'm going to get this acute angle again, and something's wrong because I know, like on the picture, that beta is obtuse. So this is just wrong. Okay, I can't do that right now. So why is that? So what's the problem here? Let's go back to what sine actually means. Okay, so sine of beta is 0.765. So 0.765 being the okay, sorry about that. So 0.765 being the y coordinate, right, of a point on the unit circle with an angle beta. So beta could be here, so that its y coordinate is 0.765. Okay, y being positive, it makes sense. But there's also another angle here, and you can see that's the obtuse angle we're looking for. Okay, which also has a y value of 0.765. Okay, so that's the angle we want. So how do we get that angle? Well, beta, okay, is going to be the arcsine, which is this value here. Okay, so if we calculate the arcsine, we're going to get the 0.49.9. That's this angle here, but that's not the beta we want. The beta we want is, maybe I should change that, the value of beta. The beta we want is here. This is the beta we want. So what we need to do is take 180 degrees, okay, and subtract the arcsine. Okay, doing so, what are we doing? We're doing, let me use a different color here. We're doing 180 degrees, but then we subtract the arcsine. Okay, we subtract the angle in blue that we just found. Okay, by taking the arcsine of 0.765. So that gives us something different. So that gives us approximately 130.1 degrees, and it makes sense, it's obtuse. Okay, and then I can keep going now. Gamma will be 180 degrees minus 35 degrees minus the beta I just found. So that's going to give me 49.9 degrees. And to find, so this is gamma being up here. And then to find, let's say let's call this C here. C, sine of gamma over C is in the same ratio as sine of 35 degrees over 6. And solving for C. C is going to be sine of 49.9 over sine of 35 degrees times 6. And that's approximately 2.69. So finally, the triangle we just found is this one. So this is 6, 8. This is 2.69. This is 35 here. This is 100.1 degrees. And here this is, what did we found? 14.9 degrees. So moral of the story is when you're taking those arcsine, make sure that you know if you're gonna get an obtuse or angle or an acute angle, because you may want to use the arcsine differently in each case.